Good afternoon. Welcome to this lecture on fluid mechanics, and the topic for today's discussion would be introduction to boundary layer theory. Now, in the last so many lectures on fluid mechanics that we have had, we were looking typically at, we stopped with Bernoulli equation, and we also had some exact solutions for the Navier-Stokes equation, right. Bernoulli equation essentially was inviscid flow. There were several assumptions that we had, and one of the primary assumption was steady inviscid irrotational flow. So, that means effect of viscosity was neglected. So, effect of viscosity was much smaller. So, it's not 0, okay, it's never 0, it is much smaller compared to other forces. So, what are the terms in the Navier-Stokes equation? We have inertial forces balanced by pressure, viscous and body, right. So, rho dV bar by dt is equal to dP by dx plus minus mu into del square V bar. So, this is also pressure form plus body force. Okay. So, you can write it in the x, y, z coordinates, and basically what we are saying is inertial, pressure and the viscous. All this while in Bernoulli equation we said this and this was neglected, and this was possible when these two terms contributed much smaller to this balance, such that the pressure and the inertial forces balanced each other. When we tried to solve Navier-Stokes equation, so we had exact solutions of Navier-Stokes equations, and we could see that solutions were possible only for 2 or 3 kind of problems, like we had this top plate, this plate fixed, and you were having a pressure gradient dP by dx less than 0. This was moving, this was fixed. Okay. This is another geometry. This gave you a velocity distribution like this gave you a velocity distribution like this, and then of course, we had for pipe flow, which also gave us a parabolic profile for laminar flow, right. And of course, certain cases like falling film, and we have film falling due to the action of gravity, so on and so forth. So, depending on the boundary condition, this could be the velocity profile, or if this were fixed, I am just drawing this fixed plate, then you could have a velocity profile like this. Whatever be it, the idea being that in order to get a velocity distribution, okay, what is the primary objective of solution of Navier-Stokes equation? We want to solve for velocities and also the pressure as a function of x, y, z and time. Okay. So, this is the objective that we are trying to do for all problems. This is what we want to get. Why do we want to get? Because from here I can get the wall shear stress, from here I can get the pumping power or loss in energy due to friction due to viscosity. As an engineer, this is of primary importance to me. I want this to be reduced. So, pumping power reduction is my primary goal. Okay. It is like for a businessman, profit. So, if you reduce the pumping power, you are reducing the wastage of energy, and because of reduction in wastage of energy, you are saving on costs, ultimately profits are more. So, this is my primary objective, which means to get the power I need the wall shear stress, to get the wall shear stress I need the velocity distribution, because I know tau is equal to mu du by dy evaluated at the wall. This is the simplest form that we have studied right from the first or second lecture of this course. And with this idea, we have always wanted to solve for this. And when we looked at these 4 problems that were seen in the course, we realized that the number of assumptions that were made to solve to get this solution for the velocity distribution were 7 or 8 or 9 assumptions, and with such restrictive assumptions only a solution was possible. And what does it mean? So, you cannot solve other problems? No, we can solve other problems. Definitely we have to solve other problems, because practical problems are far more complicated than flow between parallel plates and flow over a flow through a pipe, laminar, etc. You have generally turbulent flows. You also have laminar flows with varying various other conditions. So, the idea is we need to solve them. Now, you looked at the Navier-Stokes equation. You had terms, 4 terms on the left hand side, 1 here, 3 terms here, and then the body force term. 3-dimensional, unsteady, non-homogeneous, all sorts of difficult adjectives for mathematical solutions you want to put, you can put, and therefore, the solution becomes so much more complicated. So, what do? You said, okay, I throw off this, I get Bernoulli, which I can apply. Then I said, I look at this whole equation and then try to simplify it by making it as 1D, by making it as steady, by making it as dP by dx is equal to 0, so on and so forth, no neglecting body force. So, I reduce the number of terms and ultimately get a solution. So, the idea is we accept defeat. Okay, I cannot solve the full Navier-Stokes equation in its full form. Okay, so, what do? Cross off terms by logically explaining why they are very small compared to the others. Okay. Once that is done, you have an equation which hopefully becomes more tractable, which is probably a first order ordinary differential equation with all our coefficients being constant. So, you can integrate and get the profile, or even if it is second order, not a problem, we can try to make some approximations such that you do not have to deal with the second order differential equation throughout. You can make it tractable, make it solvable with some approximations. That approximation theory which we are going to deal with now is the boundary layer theory. Okay. Now, in fluid mechanics courses, boundary layer theory is taught separately for the external flow, and internal flow we just start using boundary layer as if the boundary layers merge and we have a fully developed flow. So, what I will do today is try to cover these in parallel, so that we know that they are not two mutually exclusive problems. The physics is the same. The fact that one of the flow is bounded on both sides, bounded all around the circumference, makes it internal. The other, because it is free on one end, is called as external flow. So, what is external versus internal flow? These are basically two types of flows which we have in fluid mechanics and in real life applications. Internal flow, all of us know, flow through a pipe, and this you can see everywhere in real life. Pipes bringing water to your house, you have in your petrol pumps, you have pipes carrying petrol, then you have underground pipelines carrying water, carrying sewage, you have natural gas pipelines, you have pipes carrying refrigerant in the back of your refrigerator, air conditioning equipment. So, any fluid which is being carried through a geometry which is confining the flow fully, confining the flow. Confining means covering it fully. So, this geometry, anything which is confining the flow fully is called as internal flow. What does it mean? Internal flow has a boundary which is going to define the geometry fully in which the flow is happening. It could be a pipe and you could have only 50% water. You could have a pipe flow which is like this, but this is also classified as internal flow. Okay, the pipe is not full, it is half full. So, this is liquid and this is air. Okay, and this is the interface between liquid and air. This is also a case of internal flow. Okay. Now, what is external flow? External flow is where there is only one surface which is confining the flow. This classification has been done in the first or the second lecture. So, there is nothing new about it. And what are the practical examples of external flow? So, I have say this table where I am sitting, and I have a fan which is turned on here, and the air blows over this table. That is the classic case of flow of air over. When I use the preposition over a surface, it is essentially external flow. When I use the preposition inside or in, it is case of internal flow. Now, over the surface, flow of air over this, you have water flowing over a flowing on, in the form of river. Okay. You have electrical wires which are connected across various cities, and you have these towers and this electrical wire which is there. So, flow of air over this, air flows over this surface, air flows around this pillar, around this geometry. It could be modified as a cylinder, and flow of air around this. So, this is a vertical cylinder, this is a horizontal, or wire is like this, flow is happening like this. So, this is external flow. Then if you think of an aircraft, very common example, the aircraft is coming out of the plane of the paper, and that means the flow of air is over the wings, it is like this. It is equivalent to a stationary aircraft and having a flow of air induced over the wings. So, this is like a flat plate. Cylinder, horizontal cylinder. Then you have of course sportsmen who use cricket ball, golf ball, tennis ball. So, this is spherical geometry, flow around a sphere, around, over, etc. would be external flow, because there is only one surface which is over which the flow is happening, everything else is infinite in all the other directions. Okay. So, that is what classifies, we can classify flow as internal and external based on the geometry. Now, what is this boundary layer? So, let us just introduce this concept of boundary layer. Short form, we typically acronym we give it as BL instead of writing all the time. What is this boundary layer? All of us know, I will explain it with respect to external flow, and then we will logically transfer all the knowledge of external flow to internal flow. So, that we see the connect and we realize that these are not two different topics, this is the same concept, same physical concept which is there, except that now we have a boundary layer developing from all directions in case of a pipe flow. So, let us look at external flow. Now, I want you to pay attention here and understand the terminologies, because this is very important in defining several terms. So, we will take the case of a flat plate, flow over a flat plate, and this is the coordinate axis, coordinate direction. This is called as free stream velocity. U infinity is free stream velocity. What is meant by free stream velocity? It means that this velocity is unaffected, the velocity with which the flow is occurring before it knows that it is flowing over a plate, okay, over a solid surface. Okay, that is why it is called free stream. This plate is extending into infinity into the plane of the paper, and we typically have the coordinate x along the plate and y perpendicular or normal to the plate. This is the typical geometry. Now, everybody knows the story, how what is happening. Because of no slip condition, you have the basic constraint we have to follow is no slip at the wall, at the solid surface. Because of no slip condition, u of y equal to 0 at all x is 0. Am I right? This is how velocity is given, u v w of course. Okay. So, velocity of the fluid at the wall means y equal to 0, that is equal to 0. Velocity is u infinity with which it is coming, you are going over the plate, and suddenly the first layer of fluid which is in contact, coming in contact with the plate, has to stop. Well, that is very difficult, right? First layer is stopping, the layer which is going at u infinity, one layer has stopped. Well, then the effect of this presence of a solid surface which is at rest is going to be propagating upward into the flow. Like, how do you relate to this? Let us say you have a typically outside railway stations and airports, there is a lot of traffic jam. Okay. So, when you start from your house, which is say 5 kilometers away, you do not realize the effect of the traffic jam. Let us say this is your station and this is the road which comes in and goes out. So, when you are coming from here, you do not see the effect at all of this traffic jam, you do not even know. But as you come closer, your speed reduces, there is lot of vehicles coming from here, the obstruction is more. So, when you come closer and closer to the cause, what is the cause? Traffic jam. Who is causing it? Because there is a railway station here, lot of vehicles are here, therefore, we are going to have a traffic jam. Okay. So, this presence of large number of vehicles is the effect is getting propagated downstream. Now, if there are 4 trains coming in at the same time, okay, let us say this is terminus station, say CST or New Delhi or whichever, 4 trains have arrived at the same time and 3 are leaving around the same time. If you have taken a flight at 6 o'clock or 6:15 in the morning, say from Bombay airport or something, it is utter chaos, because there are about 20 flights which are departing between 6 and 7. Okay, so, check-in, security, everything is so crowded. Why? Because there is a constraint there, its effect is getting propagated now in terms of time. Here traffic jam is getting propagated in terms of the distance. So, you have traffic jam at the railway station, more and more vehicles start to come in, the traffic jam will be felt till here. More and more vehicles come here, this is where you will start feeling the traffic. Sometimes you have jams up to 1.5, 2 kilometers from the place where the actual problem is, correct. So, when I am going as a driver into this flow, I start feeling this effect of traffic jam as I move closer. Okay. That is what is happening here. As I move closer to the plate, to the solid surface, what is the constraint imposed by the solid surface? Velocity equal to 0. Who why do we know that? No slip condition. Why? Because the plate is stationary. Because the plate is stationary, whatever be the velocity of the plate, let it be some small u, does not matter, the fluid has to come to that velocity. It cannot propagate, it cannot travel at u infinity. Therefore, the layers of the fluid which are adjacent to the solid surface also will, see, you were going at 50, you suddenly did not become 10 kilometers per hour, you became 40, you became 30, 20 and then went to 10 kilometer per hour. So, the speed versus distance, if I want to plot distance from home, the speed was probably like this and then went to this, and this is from where on your traffic jam effect happened, and this is your railway station. Okay. So, this effect is propagated. Suppose there was a larger traffic jam or bigger traffic jam, you would start to see this effect like this. The point being, there is no fixed location where this effect is propagating into, that is decided by the amount of traffic. Same thing, how far into the fluid. So, let us say this is the flat surface, the layer of the fluid in contact with the surface has become 0 velocity. Now, this layer which is here, will it be at u infinity, this layer will it be at u infinity, or this layer will be at u infinity, we do not know. What decides that? How far this effect is felt into the fluid stream, how far. Okay. Now, that depends on the property of the fluid, which is called as viscosity. Viscosity is what is the fact that the velocity is 0 doing? The flow is being retarded, it is being stopped completely. Because it is being stopped, there are velocity gradients which are established. The next layer of fluid obviously is not, this is at 0, the next layer is obviously not at 0, it is at a small velocity greater than 0. The following layer is at a slightly larger velocity, next one is at a larger velocity, larger, and finally there exists a layer of fluid which will be at u infinity. Why? Because this layer of fluid, let us say this is the nth layer of fluid, does not know that there is a solid wall here. So, if you are here, you do not know that there is a traffic jam. If the moment you are coming here, you know there is some traffic jam. The moment you are here or somebody coming from this part, they know they are entering a big time traffic jam. So, where you are with respect to the cause, railway station, flat plate, no slip condition is the cause. Okay. Where you are with respect to that will decide whether you are going to be slower than u infinity or equal to u infinity. Am I clear? Now, this location at which the velocity, local velocity x comma y divided by u infinity is 0.99. Typically, we do not like to have anything as 0 and 1, we like to have it asymptotically going to 1. So, if I expand this diagram for you, this is the flat plate, this would be the profile. This is called as the velocity profile, velocity distribution, whatever you want to call. And of course, our coordinate axes remain, this is y, this is x, and the arrows here indicate the direction, length of the arrows kind of indicate the magnitude. So, what does it mean? This is 0 velocity, slightly higher. Finally, this layer is at u of x comma y is 0.99 times u infinity. Okay. So, we do not want 100%, we say location, I am going to define what this is, location where velocity of the fluid is 99% of the free stream velocity. That point is very important to us. Okay. I will complete this sentence in another minute. Why is it very important and what is it called? So, if this is your flat plate, this is your beginning of the plate, leading edge, this one. I am coming from here, I am a particle, let me go back to this diagram, I do not want to spoil another diagram. I am a particle of fluid which is happily coming here. Okay. I am walking over the plate. When I reach this x is equal to 0, I may not be affected, but at some distance into the plate, I am flowing over this surface, this is the beginning. I come to this point, I am more used to the traffic jam, I am more used to the fact that there is a plate below me. I come here further, I know that I do not have a choice of getting out, I am stuck in the traffic. I come same x, same y, I come further into the plate, I know that this solid flat plate is going to bother me. Further, it is going to bother me more, right. That means, as I come along the x direction, as I move, the effect of viscosity which is retarding the flow starts to be felt more and more, because the the fluid has now gotten used to the fact that there is a solid plate below it, which is at u is equal to 0. So, no slip condition means u is equal to 0 at the wall. At x 1, x 2, x 3, 3 locations I am taking. This particle of fluid here, this particle of fluid here, this particle of fluid here are going to be very, very different in terms of what they see. Though they are at the same y location, let us say particle A, B and C, A is at x 1 y, B is at x 2 y, C is at x 3 y. Y coordinate is the same, let us say y, y 1 let me keep, because we are talking of a variable. What is happening? This particle may not even know that there is a boundary layer, there is a solid plate, because the velocity has reached 99% of the free stream velocity here. This particle also may just escape, because the free stream velocity has reached 99% here. This one may be way inside a location where I might say u c of x 3 comma y, let us say would be 0.9 or 0.8 u infinity, possible. This indicates that it is slower than u infinity. What I am trying to tell you is, the locus of points which are having 99% of the free stream velocity, they are not going to be at the same distance from the wall. At a location x 1, 99% happens here. At a location x 2, 99% happens here, let us say. So, when I join these points, this will be called as a boundary layer edge of the boundary layer. Edge of the boundary layer, basically I will draw this again and make it nice, so that we do not write anything there. This is the solid surface, this is the edge of the boundary layer. What do I mean by the edge? I will just tell you in a minute again. This is your coordinate system y x, u infinity is the free stream velocity, locus of points whose velocity u of x comma y is 0.99 times u infinity. So, you join all the points along various actual locations x 1, x 2, x 3 etc. This one is here, this one is here, this one is here, next one would be further there. You join all those, you get a line which is called as the edge of the boundary layer, and this region is called as the boundary layer. Okay, great. So, what? Well, something very, very important, very, very useful, very, very thought provoking happens because of this separation of the because of the segregation. I do not want to use the word separation, because separation in fluid mechanics means something else, because of the segregation of the flow into two regions. What are they? So, let us understand, appreciate, assimilate whatever I am trying to tell you. If I draw a velocity profile at this point, so it will be like this. What will be the velocity after this? Constant, almost constant, because it is 0.99. So, it is slightly going to increase. What about the velocity here? U infinity is same. So, like this, and then it will be almost constant. What about in this region? This is u x comma y, this is u x comma y. And you see that every point inside the boundary layer has u of x comma y divided by u infinity is less than 0.99. Why? Who is causing this reduction? Property of the fluid called viscosity. So, this boundary layer is essentially, edge of the boundary layer basically is a line which separates. Please imagine this as a plane, okay? It is like a bed sheet which is going into the plane of the board, plane of the paper. So, this portion below this is the region where viscosity effects are more. So, this is the viscous region. Very important classification. Please make a note of this. This is where viscosity effects are important. Why? How do I know it is important? Because I see this. Okay, because I see this, I know viscosity is important. This part, this is called as free stream, because it does not know any point here, any point here, any point here, does not know that there is a solid wall, it is still flowing with the velocity u infinity. And what is the approximation? What is the fact here? Inviscid approximation. What does it mean? Viscous force, please remember, viscosity does not become 0 at all. Again I am repeating, viscosity is constant, not equal to 0 ever, but viscous forces are important inside the boundary layer, are not important outside the boundary layer. That means what? The boundary layer basically segregates, demarcates, distinguishes the flow field into two parts. This is the flat plate, this boundary layer is doing this. This part below the edge of the boundary layer is completely viscous. You have to have viscosity terms here. The part above is inviscid. It can be treated with viscous effects tending to 0. Okay. What is the big deal? What is so great about it? I will just show you writing the Navier-Stokes equation, and you will realize why this is so important. Well, what is the Navier-Stokes equation? I will just write one. Which equation is this? This is the x momentum equation. So, this is minus dp by dx plus mu and I neglect the body forces. So, this is my equation. What are these forces? Inertial. What is this? Pressure. What is this? Viscous. What is happening? If I were to solve this full equation for the region, what is the flow field? Y some capital H. I am just drawing this diagram here. This is some capital H, huge region. Okay. I have to solve keeping this term also. Now, because of what Prandtl did, this concept of boundary layer was because of our great fluid mechanician Ludwig Prandtl. Because of what Prandtl did, he said viscous effects are important only inside the small region which is called as the boundary layer region. The symbol for this is delta. Boundary layer thickness is given by delta of x is local boundary layer thickness. Why do we call x? Why do we have a bracket x? Because this boundary layer thickness is progressively changing as I move along the flow direction. Okay. So, that is why it is a function of x. So, what we are saying is Prandtl, because what he did, we have split the region as 0 less than y less than delta and y greater than delta. And in the case of y greater than delta, what do I have? Inertial forces balanced by pressure forces. No viscous effect. What does it mean? My equation would be rho du by dt plus u du by dx plus v du by dy plus w du by dz is equal to minus dp by dx. And of course, we make several assumptions steady and then this two dimensional, so on and so forth. So, we would have in the free stream, this is called as the free stream, correct. This is called as the boundary layer region. Free stream, u is equal to u infinity, therefore, v is equal to 0 by continuity equation, correct. Why? Because continuity is du by dx plus dv by dy plus dw by dz, incompressible continuity equation. In the free stream, this is 0. Why? Because u is constant, which is u infinity. This was two dimensional, so this went to 0. dv by dy is equal to 0. v is equal to constant or function of x. At x is equal to 0, v is equal to 0. So, v is 0 throughout. So, everywhere in this part u is u infinity, v is equal to 0. How nicely our Navier-Stokes has split. Navier-Stokes now will just be u infinity du infinity by dx is equal to minus dp minus 1 by rho dp by dx. This is if u infinity is constant. You can also say u infinity is constant, not a function of y. So, this goes to 0. So, the point being a complicated second order partial differential equation now has become so simple outside the boundary layer. Yes, I have to solve this entire thing for a very, very small region. Full Navier-Stokes has to be solved. For a small region, which is between 0 and delta x. Isn't it lot easier than going from 0 to full h? And mind you, boundary layer thicknesses are of course very, very small, but what is so great about it? All activities, all action, let me call it, all action with respect to viscosity happens within that small region. So, I need to study that part only in detail, and the part beyond that is actually not so important as far as action is concerned. What do I mean by action? Mu du by dy. Beyond delta, I told you gradient is 0 because velocity is constant. So, this gives rise to shear stress, this gives rise to power. Whose in what region is this important? This region is what we call as the boundary layer region. This region, if I solve properly, I get as an engineer what all things I want, I will get from this region. I do not have to worry about the region beyond y equal to delta, and therefore, I have savings in computational time plus of course, cost plus effort, and of course, chances of mistakes are more if you are going to deal with a huge region where the activities are going to be, all the activities are going to be important. Okay. So, this is the idea behind the concept of a boundary layer. The boundary layer that we are talking about is called as velocity boundary layer or hydrodynamic What do you mean by this? Velocity means it is because of viscosity given by symbol delta of x. That means obviously there is something else. The other thing that you will see is called as thermal boundary layer, which you will do in heat transfer, which is given by symbol delta sub x t. So, if this is a flat plate, this could be your delta of x and this could be your thermal boundary layer, or your thermal boundary layer could also be here. That takes us to a different world altogether. Heat transfer is defined based on certain thermophysical property by which is called as Prandtl number, and Prandtl number dictates whether this delta T would be above or below delta x. So, that is beyond the scope of our fluid mechanics course right now. So, this is something which we need to remember, appreciate and accept. Okay. Now, having understood what this boundary layer business is, let us just translate our understanding of boundary layer for external flow to what happens inside a internal flow situation. Now, internal flow, if I said it consists of a confining wall or solid surface all around the flow. That means, I will have to draw it like this. Two walls I have to draw. Basically, wall is there everywhere, but to show us here I have to draw two walls. So, and let me hope that my circle is coming out correct when I try to draw this circle. Okay, not bad, not so bad. Okay, the flow is coming here with a velocity u infinity, and the coordinate system, unlike there, we will call it, this is r, this is x or z, some books will call z, this is the radial direction and this is the axial direction. So, this and this is the theta direction. So, azimuthal means theta. Okay. Now, cause for formation of boundary layer, presence of a solid surface which has a velocity different from the fluid velocity, correct. Now, here the fluid is entering a geometry, the fluid is entering a geometry which is like this, is entering. Because the walls are stationary, the fluid which is coming in will now touch a wall which is at 0 velocity, entire fluid. So, it is like a sheet which is going to get covered with a layer of fluid. Okay. The solid wall will be covered by a layer of fluid which is at 0 velocity. Then exactly the same logic we will apply. A layer of fluid at a distance slightly above the wall would have slightly positive velocity, further. But now, in case of internal flow, you need to imagine that this process is happening all around the circumference. So, a boundary layer is being formed all around the circumference. So, it is as if, let me try to show it to you, it is as if this is a, if you have a sheet, a rubber sheet, and you try to press it in, puncture it inside, it will go inward as a, like a, with a shape like this, right. So, this was the original position of that sheet. When I apply a force here, it will go in from all direction in 3-dimensional. That is exactly what happens in case of internal flow. The boundary layer is formed all around the circumference, all around the wall, and what you see is that this boundary layer which is formed will eventually come together at some distance from the wall. unlike external flow where the boundary layer was continuously growing, if I want to put it mathematically, d delta by dx is always greater than 0, correct. Boundary layer thickness is progressively increasing along the flow direction. Now, what are we seeing here? In case of internal flow, there will be a region after which the boundary layer has merged. Boundary layer merges after a particular distance. This point where the boundary layer merge, that means what? Let us understand again from our external flow discussion. What is this region? Viscous. What is this part? Inviscid, correct. This part is the inviscid part, this is the viscous part. What do you see? Inviscid part, inviscid region decreases and finally is no longer present, correct. Goes on decreasing, and then at a point where this boundary layers have merged, the inviscid region is no longer present. The entire flow after this point completely viscous. I hope you are able to appreciate this difference here. No matter where you are in the flow, the flow field is segregated into two regions. Viscous, edge of the boundary layer creates this demarcation, viscous region here, inviscid part above it. Whereas, in case of internal flow, after a certain distance from here, this is say z equal to 0, x equal to 0, this point where the boundary layers merge, you have a completely different problem. The flow is completely viscous, there is no inviscid core here, and that is what makes internal flow very different from external flow. The fact that boundary layer reaches the maximum height. What is the maximum height of the boundary layer? Radius. So, d delta by dx is greater than 0 until where? Until this point. D delta by dx equal to 0 for x greater than LH. Everybody agrees with me mathematically? It is growing until L subscript h. Afterwards, there is no boundary layer, or you want to say the boundary layer is of constant thickness, the viscous forces are going to be present throughout. Okay. So, because of this change in the flow characteristics from partly viscid, partly inviscid to completely viscous. What happens to my Navier-Stokes? I am not writing the cylindrical form of the Navier-Stokes. All I want to tell you is, unlike here where I could split, where I could drop off the viscous forces terms, outside the boundary layer. Here I have to retain this. So, inertial is equal to pressure plus viscous. Everywhere beyond x is equal to LH, and this location where the boundary layer merge is called as the entrance length, entry length, hydrodynamic entry length, developing flow, all these are meaning the same thing, do not get confused, these are all meaning the same. What is special in this part? You have both viscous plus inviscid part. Beyond this point, beyond this region, x greater than LH, flow is completely viscous. Full Navier-Stokes has to be solved. Of course, with assumptions, simplifications. What do I mean by full? Means all forces have to be kept. You cannot drop off any force. You can make assumptions of steady, one dimensional, two dimensional, etc. Those can be done, but the nature of the equation would be both inertial, viscous and pressure forces. All three have to be taken into account. That is, inertial forces balanced by, this is the right way to put it, balanced by pressure plus viscous. What is it here? Again, let me go back here. Inertial force balanced only by pressure forces outside the boundary layer. Here in this part, inertial balanced by pressure plus viscous, that was inside the boundary layer. I hope you are able to appreciate how suddenly because of the presence of a confining wall, how suddenly the flow has changed, the flow characteristics will change. And what is so important, what is so useful with this boundary layers merging is that, I will just tell you, let me just draw a nice simple diagram. Let us say the boundary layers merge here. Please appreciate this fact what I am telling and try to understand. This is the look in this part, till this part your inviscid was decreasing, viscous effect was increasing till this region. What about this part? Inviscid 0, not there, viscous constant all over the pipe, all through. That means, if I take some measurements here at x1, another measurement here x2, another measurement further downstream at x3, do you think there will be any change in any characteristics of the flow here? Why? Why should there be any change? The flow is going to not know whether it is here or here or here, because nothing in the flow with regard the forces is going to change. Boundary layers have merged, viscous effects have propagated to the center, flow is completely viscid, inertial forces are the same, everything is the same. This region is called as fully developed flow. All through. That means, no change in any forces, which means what? Velocity, viscous forces change means velocity gradients has to change. Nothing is changing, velocity gradient is same, so velocity profile is constant. Along x direction. Very, very important. What does it mean? I will show it diagrammatically. Velocity profile does not change along the flow direction. So, if I keep it here, this is where the boundary layers have merged. the velocity distribution taken here, velocity profile taken here will be the same as the velocity profile taken here. Identical, sorry they are not identical because I have drawn it. So, identical profiles both in shape and magnitude. U at x1 r is identical to u at x2 r, means du by dx is equal to 0 is a mathematical representation of fully developed flow. Why is this correct? Because in this region the forces that are going to act are viscous plus pressure is equal to inertial. Nothing is changing with regard the inviscid and the viscous region in this part. Why? Because the boundary layers have merged. There is no preference to anything here, you just have the flow completely viscous here. So, whatever was the characteristics at x1 would be the same as the flow characteristics at x2 and x3. So, velocity profile therefore, gradient of the velocity profile does not change, which means the velocity profile does not change. What is the gradient? Du by dr at r equal to capital R, mu du by dr at r equal to capital R. This is shear stress. If this is constant, that means this is constant, correct? This is constant, then this is constant, which means the profile is identical. That means profile at every location is identical. That means du by dx, please remember du by dx along the flow direction is 0. That is the mathematical representation of fully developed flow. Okay. Now, let us go back to our external flow. Will the flow ever become fully developed in this part? Is the velocity profile going to change at every axial location, or is it going to remain the same? Unlike internal flow, the velocity profile at every point in the flow direction for external flow is going to vary. I will just show that to you and then we can stop. However long it may be, this is the profile, this is the profile, this is the profile. Going from 0 to 0.99 u infinity, let me just draw it like a triangle and I superimpose x1, x2, x3. Let me just show you how they will look. This is 0, this is 0.99 u infinity. I am just showing it as a triangle here. This is at x1. The black one is at x2. Let me say, just to go to this. This is at x2, and then the green one, which is, sorry, this should be exactly the same. Sorry, the green one would be at x3, which is going to do this. This is at x3. You can see here that the velocity gradients, the blue one was for x1 location, black one was for x2 location. It takes a greater distance. So, let us say this is delta 1, black was delta 2 and green was delta 3, or what was the velocity? 0.99 u infinity. All of them reach that value. So, what is the gradient? For the blue one, the gradient would be 0.99 u infinity by delta 1. For the black one, it will be 0.99 u infinity by delta 2, and for the green one, it will be 0.99 u infinity by delta 3. Delta 1 less than delta 2 less than delta 3. Therefore, this one is like your tau 3, this one is like your tau 2, equivalent. Of course, you have to multiply by mu, etc. It is equivalent. What I am saying is numerator is the same, denominator is increasing as I move along the flow direction. This is my flow direction. As I move along the flow direction, delta is increasing, delta appears in the denominator. So, the shear stress is going on decreasing, whereas here shear stress is equal to constant. I hope you are able to appreciate this thing again. Shear stress is constant, shear stress is going on decreasing as I move along the flow direction. Okay. So, with this we can stop today's lecture, where we talked about concept of hydrodynamic or velocity boundary layer. We saw why a boundary layer is being formed. Boundary layer is formed because of the effect of the fluid property called viscosity. Boundary layer basically segregates the flow space, flow region, flow field into two parts. One part which is closest to the wall, where the effects of viscosity are going to be present, is called as the viscous region. Beyond the boundary layer, it is going to be called as the inviscid region, where velocity is constant, which is the free stream velocity. This is for external flow. Now, internal flow is slightly different. The boundary layers merge after a particular distance, because it is formed all around the circumference of the pipe. Location where the boundary layers merge is very important. We call this as an entrance region, hydrodynamic entrance region, entrance length. Beyond that is where all the activity happens. We call that as a fully developed region. In fully developed region, because nothing is changing with respect to the forces, the gradients are the same, which means the velocity profile is the same. That means, for fully developed flow internal, you have du by dx equal to 0, wall shear stress is constant everywhere. So, if I were to plot this shear stress as a function of x, I would do this for pipe, and for external flow continuously decreasing. Whereas, in case of external flow, because the boundary layer thickness is going on increasing, there is no concept of fully developed flow. The shear stress goes on decreasing, because the gradient starts to become small. One last thing is, in external flow, we had, this is external, this is internal, we had idea of u x comma y and u infinity. Whereas, in internal flow, we had u r comma x, which is same as x comma y. We do not have anything like u infinity. We have what is called as bulk mean velocity. Bulk mean or average velocity, this is free stream, and this is obtained by mass balance of the flow at any section. This is the bulk mean velocity, we say, green one, u bulk mean, this is u of r comma x, and we say by mass balance m dot rho into cross sectional area into bulk mean is integral rho u r comma x dA. So, this is like a pseudo number which you create. So, u bulk mean is equal to 1 by rho pi r square. This is rho u of r comma x 2 pi r dr 0 to r. Rho's cancel, pi cancel, you would get u bulk mean is equal to 2 by r squared into 0 to r integral r u of r comma x dr. So, knowing the velocity profile, I will be able to get the bulk mean or average velocity, and whatever is the role of u infinity in external flow, bulk mean velocity takes that role in case of internal flow. Thank you so much.